welcome you all to the first class on defects in materials. In the earlier class, I had given a brief introduction about the syllabus which is going to be followed for this course and what exactly will be covered in this particular course. Okay. As I mentioned in that class, the first thing which one has to understand is that the title itself means that we are studying defects in materials, and mostly we are talking about crystalline materials. If we wanted to study defects in crystalline material, okay, first we should have a reference standard which is a material which does not contain any defect. That is the first criterion which we have to meet it. So what we should know is how to generate a perfect material or a perfect crystal which does not contain any defects, or it is an ideal crystal. Okay. This ideal crystal can be generated, okay, by looking into International Union of Crystallography table which is available. From that, if we know the space group of a particular crystal, then we can look at it and then try to generate the crystal structure. But if we have to do that, what is the criterion which first we should know how this table itself is generated, what are the important significance of it. Only then we can understand and then utilize it in the best way, right? Okay. So this is what will be covered in basically in a lecture which we call it as generally we call this field as crystallography. So crystallography studies, okay, the arrangement of groups of atoms or molecules or motifs or patterns in a periodic way, okay, in 1, 2 or 3 dimensions. Okay. But what we will talk about it is that generally in crystallography, this is also called as geometric crystallography. The reason essentially is that suppose an element is there, what is the way in which it is going to, which crystal structure it is going to form. That information we can't get it from a geometric crystallography. But geometric crystallography tells what are the options which are available for it. If it has to form a crystal, what are the crystal structures to which it can form. Okay. Only those. So geometrical crystallography is nothing but a sort of a probability of looking at what are the structures which we can form. This comes on the basis of what is the type of symmetry which is associated with the different type of crystals. So what are the possible type of arrangements which we can have. That is what we talk about in this geometrical crystallography. Let us look in some patterns in 1 dimension, 2 dimension, okay, see what we can understand from this. Okay. So though we wanted to construct crystals in 3 dimensions, it is better to start from, because there are some crystals which are there in 1 dimension also, 1 dimensional periodicity. There are, like if you look at surface of a material, a surface of a material is a 2-dimensional crystal, then bulk crystal is a 3-dimensional crystal. So it is important and in our interest to know what all types of periodicity exist in all these 3 dimensions. Okay. Let us just look at this pattern. When we look at this pattern, okay, can you make out whether any periodicity is there in the first pattern? What do you see? Yes, there is some periodicity is there. Okay. So some pattern is getting generated, okay, is there, and that pattern repeats itself, correct. In the second one and the third one, if you look at it, the second one it is very easy to make out that what is the pattern, but in the first one it is a little bit difficult. The third one, if you look at it, the type of pattern which is getting repeated is not one, because like here it is a this is the motif which is getting repeated, or the pattern which gets repeated. In this particular design there is only one which is getting repeated, okay. So that means that the pattern which repeats itself, we call it as the motif. So this is the motif in these 2 cases, these are asymmetric motifs. When we say something is asymmetric, that means that there is no symmetry which is associated with that motif, correct. Now if you look at the second one, the motif which repeats, okay, that motif itself has got some symmetry associated with it. So what we can have is that motif itself can have a symmetry, or the motif itself can be there without any symmetry, which is called as an asymmetric motif. Okay. Using an asymmetric motif, using some symmetry operations we will come to know later, that different types of motifs could be generated. Okay. Now let us look at this pattern. It is a pattern in 2 dimensions. This design, if you look at it, the first one is taken from a wallpaper design, okay, packing paper design. Here if you look at it, the pattern which generates or the pattern which repeats itself is essentially the one which is shown in that white square. Okay. How is it getting repeated? By keeping one on top of the each other, okay, we can generate it. It looks like a square pattern. This is one which is taken from a cloth. Here again you can say that this is the one which is a motif which is getting repeated again and again. Okay. In both the cases what we have is a square type of pattern, but the motifs are 2 different types of motifs. So it looks like 2 different types of a design. So in nature if we look at it, even when we look at various types of designs, but when we look at it for, especially if we take with this example itself, that though different types of designs we can see, what is getting repeated is many of them are common. Now the question which arises is that, is there any restriction or how many types of periodicity which we can have in 1, 2 and 3 dimension? That is the information which we require. Okay. So just suppose we have to represent this pattern which is getting repeated. How can we go about and do it? Okay. Because the pattern itself or different designs are, if you look at it, is an asymmetric pattern in this particular case. It is a pattern which is very complicated. The best way to represent it is, if you wanted to look at periodically and to look at the periodicity and work on it, the best thing to do is to represent it by some point. So that is what we have done, is represented with a point, correct? This is the point which repeats itself. This point could have been placed anywhere, it does not matter, but it will show the same. And if you place a particular point at this corner, everywhere it should be placed as that particular corner. That is how the lattice has to be generated. Now we can look at the periodicity of the lattice, because that is much easier because we have removed the pattern. Okay, once the pattern has been removed, we can very well see only the what is getting repeated. Okay, and when we look at this periodicity and when we look at the periodicity in the pattern, one thing which you have to, if 2 dimensions or 3 dimensions, we have to use coordinate system to represent the axis. So the convention which is followed in crystallography, okay, I thought that right at the first instance one should understand what is the international convention which is being followed in the books on crystallography. If we follow that convention, it becomes much easier to understand the books. Okay. So what essentially is done is that from top to bottom, okay, is how the x-axis is defined. Okay. Y-axis is from left to right and z-axis is coming out of the screen. Okay. This is the convention which is being followed to represent the origin, okay, and the different axes. Now if you look at it, when the pattern gets repeated, what is the shortest vector which is getting repeated? Okay, that is from one lattice point to another lattice point, and this is the distance which it is getting repeated. So if you represent it by a vector A, so this is the lattice parameter, correct? So the pattern which is getting repeated is what we call it as the motif. Okay. The motif could be asymmetric or it could be some symmetric motif. Okay. So motif itself could have symmetry. We will come about symmetry little bit later. Okay. And this motif could be essentially in an art form, it is a pattern. In solid state physics, if you look at it, we look at position of atoms. Okay. single atoms or groups of atoms. Then in chemistry, if you look at it, we talk about molecules, okay, various types of molecules. The molecules itself will have some symmetry associated with it, right? Okay. Then this motif gets repeated, okay, or the motif which is getting repeated, when we represent it by a point, we call it as a lattice point, okay. What is the periodicity which is underlying this lattice, okay, is what is described by the lattice, okay. In the pattern, what is the periodicity which is getting repeated, that we can show it, okay, by essentially the lattice. Then lattice point generally we assume to have 0 dimensions and infinite symmetry associated with it, and lattice is supposed to be infinite in all directions, okay. So surface effects do not come in the lattice, but in real crystals always that will be there. Surface effects are very important, okay. And the shortest translation vector, okay, in different coordinate axis directions, we call them as the lattice parameter. Okay. Now, from this what we can understand, when the pattern which is there, which is getting repeated, okay, we can call it as a design. That is the terminology which I am using it, okay. In crystallography, we will call it as some crystal, okay. The crystal itself, when we are trying to represent it, we have a lattice, and around each lattice point we have a motif which is been put around it. So lattice plus a motif is what a crystal is, okay. In some books you will find that instead of motif, the terminology basis will be used, okay, and it can be represented by a vector, okay, r equal to u into a, it is written. A is the shortest lattice translation vector, okay. U is the number of times it gets repeated to reach a particular lattice point. This is in one dimension. Similarly, we can write it for 2 dimensions as well as 3 dimensions, okay. What I had given here is that instead of a pattern which is an art form, we can use some symbols also. Like generally in books, if you will find, they will use a letter like P or R to represent an asymmetric motif, okay. In this case, I had used P, and I can represent it P by a lattice point at some dot, and this repeats itself. This is one way to look at it. Another, if you look at it, there are 2 types of asymmetric motifs are getting repeated in the next crystal structure which I had considered, P and R, okay. But these 2 are 2 asymmetric ones, they are close each other, but if you look at it, you do not see any symmetry between them in the motif. The next one is one where I have a P and an inversion of, not an inversion, a mirror of P is also there, okay. These together constitutes a motif that repeats itself. This is another type of a structure which we are looking at it, okay. From this itself we can understand that even in one dimension we can have some symmetry around the motif, okay, which can repeat itself. But what all types of symmetries which we can have, which can repeat itself, we will see shortly. Before going further, first let us look at periodicity in one dimension. So what I have done it is I had given some more examples here, okay, one dimensional lattice where I have taken an atom, okay, 2 types of atoms, one with open circle represents one atom, closed circle represents another atom, okay. Then different ways in which it is getting repeated, okay. This I had just generated so that one can work out and find out what is the lattice parameter, okay, what is the motif which is associated with which is repeating itself. All this information one can work out, okay. Now let us look at the symmetry in a lattice, okay. Just if we look at this lattice itself, the first thing which we see it is that there is a translational symmetry which is associated with it. If I move from one point here to another point here, okay, after the movement it is at an identical position. So in an infinite lattice we will not be able to make out that we have moved it, correct. So this symmetry we call it as a translational symmetry. Suppose around this point I just try to rotate it by some particular angle, what will happen? It will come to a position which will be inclined with respect to this, but it is distinct. So, it is not coming to a position which is identical with itself. Okay. So, then that point here does not have any symmetry. Suppose I rotate it around this by 360 degree. It comes back again to original position. Though we have given a 360 degree rotation, okay, the present position and the earlier position, we are not able to distinguish them. That means that this is in mathematical terms, this will be called as something which is invariant. Whatever you do, it remains, it appears the same. Okay. And similar to one-fold, around this if I give a 180 degree rotation also, then what will happen? It will just come back again to the same position. I can give an 180 degree rotation with respect to midway between the two lattice points. Then again what is going to happen is that 180 degree and this point will be moved to here, this point will be moved to here from one position to another. So, essentially again if you look at this as a two-fold symmetry which is associated with it, correct? Okay. So, now we can see a two-fold symmetry. Is there any other symmetry which we can see in this pattern? Okay. No? You just see this. What I have done it is here, now I had how this symmetry is represented, a two-fold symmetry is represented with an ellipse. So, I had just marked it at this lattice point and another one which comes at in between. Okay. Now, you see this is a one which is a symbol for showing a mirror. If I put a mirror like this, then this atom position, okay, will be getting reflected here and this position gets reflected here. That means they are coming back to identical position. So, we can have a mirror passing through the lattice point. Now, is there any other position we can put a mirror? Like in between if I put it, now you see that it is again getting reflected. Okay. So, these are all the two positions we have, one at the lattice point, one in between. Similarly, for rotation also one at the lattice point, one in between, we have a two-fold rotation. Okay. So, let us consider this particular case which I put a mirror somewhere else in between arbitrarily. Okay. Then, if I look at it, then this atom position will be getting reflected from here to here, which is not a lattice point, and this position will get reflected from here to here, which is not a lattice point. So, if we put a mirror plane at some position arbitrarily, it doesn't. That means that from this we can understand that once a lattice is fixed, where all we can have the symmetry elements also is decided. We can't have everywhere, anywhere we can put an axis, and different points in the lattice will have different type of symmetry. That is, apart from this particular one, mirror symmetry we can have it at the lattice point and midway between. Similarly, what is true for two-fold rotation, in between regions, whichever we take it, okay, there is no other symmetry is there. This what I have done it is just taken across from one lattice point to an adjacent lattice point. Here I had shown the various symmetries which are same. Okay. One is a two-fold symmetry, that is around each lattice point we have a two-fold. We have a mirror, two-fold rotation and a mirror, and then if we look along this, if we take a mirror, then also it appears to be the same. So, that will be there. Okay. Then in addition to it, at the center we have a mirror which is generated, and similarly a two-fold rotation. This is all which we have. We extend the usage of how we talk about in terms of 2 dimensions and 3 dimension unit cell, then we can call this as from one lattice point to another adjacent lattice point as a unit cell in 1 dimension. And these are all the symmetry which are can be seen in unit cell in 1 dimension, correct? Okay, what are the symmetry elements even in this 1 dimension? Now we have seen in the lattice there is a translational symmetry, there is an one-fold rotation, there is a two-fold rotation, then we have a reflection. And this rotation, rotational symmetry and reflection symmetry are consistent with the translation, because then only the invariance will come, correct? So, just looking at this slide from whatever I have explained, I hope you have got some idea about symmetry, what symmetries are, which we will consider later in detail in 2 dimensions and 3 dimensions. Okay. Suppose we wanted to construct a crystal, what should we do? The best way to do it is to put a asymmetric pattern or an atom or a group of atoms around each of these lattice point. Okay. Let us do that. If you put an atom, an asymmetric pattern around each of the lattice point, now if we look at it, this becomes a crystal. In this crystal, okay, only one fold rotation is there along x axis, y axis as well as z axis. Okay. So, this is written as it is a primitive lattice with 1 1 1, okay, that is x, y and z axis, they are symmetry, and it is represented as P1. Now, if I take a motif which has got a 2-fold rotation, okay, and then I place it around each lattice point, now a crystal which has been created. Now, this crystal, what is the symmetry which it has? It has got a 1 fold along x axis, because if you rotate it by 360 degree only it will come back. Along y axis, again another 1 fold rotation. Along the z axis, that is perpendicular to a screen, we have a 2-fold rotation, right. So, this is represented as P112 this way, and short form which is used as P2. Suppose I take a mirror image of this asymmetric motif and make that as a motif and put it around each of the lattice point. Now, we can see that along x direction we have a mirror, y direction there is 1 fold, z direction there is only a 1 fold. So, now what we have is that PM11, okay. So, this represents PM. Suppose we take the same this lattice and put a mirror, okay, along this lattice direction, and then what is going to happen is that every lattice point, every motif, now we can see that a mirror image is being formed. We assume we consider this to be a motif which repeats itself, correct. So, this if we represent it, x direction there is no mirror symmetry, only 1 fold, y direction there is a mirror, z direction only 1 fold rotation. So, this is what we represent as P1 M1, okay. This is also, if you look at the general symbol which is used PM, because only one mirror symmetry is there. Now, if you look at it here what we have done it is, this motif which we have taken a along the lattice plane, along the lattice direction we have put a mirror, and then when we have created, now we can see that we have 2 mirror planes are there perpendicular to each other, and then along the z direction there is a 2-fold rotation is also present, correct. So, this is around every lattice point it is there. In addition, in between also a similar type of a symmetry which gets repeated. So, the symmetry which it has is now PMM2, or it is generally written as P2MM, okay. This is how generally it will be written. Last one, okay. Here if you look at it, this is a motif, okay. Around the lattice point I put a mirror along the y direction, then all these points get reflected here. Now, I look around each of these can be considered as a motif which is getting repeated itself. Now, I look around each of the lattice point, what is the symmetry which is available. This P gets 2-fold rotation, it will come here around the z axis. This one will get 2-fold rotation which is going to be there. Then along this if I put a mirror, okay, now what I have is that there is a mirror which is there, mirror symmetry. In this direction also there is a mirror symmetry is there. So, along x direction now we have a mirror, y direction there is a mirror, z direction there is a twofold. So the symmetry which we have is that P mm2 we write it, primitive mm2 P. Yeah, the lattice when it gets repeated, okay, the number of lattice points per unit cell, if you look at it, that's only 1. Because any lattice point, if we consider it, it corresponds to one as well as the other. If I take a lattice, as I mentioned, two adjacent lattice points, this point will correspond to this side and on this side. This lattice point also got this side and this side, 2 into half. So the number turns out to be 1. So it's primitive, and generally one should remember at this stage that small p is used to represent primitive in 1 dimension and 2 dimension, and capital P is used always in 3 dimension. Okay, it's clear? Okay, let us proceed. So far we have considered all the operations are called as point group operations, correct? It's only around a point we have looked at what all the type of symmetry elements. Okay, so these are all the type of 5 point group symmetries are possible even in 1 dimension, right? Now let us look, can we have any other type of a symmetry which is possible other than this, okay, for the crystal. Here what I have done essentially is taken that lattice, okay, which essentially this particular lattice, if I shift the bottom portion by a by 2, then all the atom positions will be coming at in between, right? Bottom portion, top portion remains that same. That is what exactly which has been done. And what is the direction in which it has been done? It has been done along the y axis, right? Or I can show that this is around this axis, okay, a shift has been given, and around this axis a mirror image also has been created. It is equivalent to, I shift this P from here to a by 2 and then take a mirror, then this will be created. Again shift it by a by 2, then take a mirror operation, it will come, and from this point to this point is where the periodicity is occurring. Okay. This type of symmetry operation, we can see it only in lattices, not around points. So this is called as a glide symmetry. Okay. Glide symmetry is one where we have done an operation of a mirror and a translation, correct? In the other case, what we have done is, most of the cases where we consider it is, we are doing a symmetry operation of a mirror which is consistent with translation so that the structure looks identical. Whereas here there is a translation which is involved. There is a combination where rotation and reflection which is consistent with translation. Here what we have shown is where we have a mirror plus a translation. Okay, this is the subtle difference between these two. Similarly, the other option which we have is that, which does not work in 1 dimension, is that, okay, we can have a rotation and also a translation. That will become a screw axis. This we will see it only in 3-dimensional structures, not in any other structure. Okay? That will come to later when we talk about 3-dimensional structures, we will mention about that. Here what we have done it is, again, as you remember the one which has got the P mm2, okay. This is one part of the motif, the other part of the motif was here. Now we have shifted it, right. When we shift that motif, okay, by a by 2, then it occupies a position where it is nothing but a glide again is going to be there. Now we have a mirror in the x direction, right, and the y direction there is a glide, and then we have in between these points we have a twofold rotation is also there. So this symmetry is PMB2 is written. What does B means? At this point, M denotes mirror Okay. If there is a glide along A axis, it is generally denoted by a letter A. On B axis, it is written by a symbol B. Okay. So that is why the PMB2 represents the twofold rotation, and this is generally represented P2MG. G is for glide. That is the symbol which is being used. But here what we have done, we have the detail of glide is along which direction. Then we have to mention that it is a glide or a B glide or a C glide. So this is details of all the symmetry elements which are there. This is a general notation, right. This we will be followed in 2D as well as 3D. It is equivalent to 3 dimension we call space group. Okay. So here we have 7 one-dimensional space group, we can say that. Okay. Point groups are 5 and space groups are 7. Okay. So what are important things which you could which we have studied so far? That is, even looking at a simple one-dimensional lattice and a one-dimensional crystal, we have got information about the lattice, about the motif, okay, some idea of what motif, some definitions we have looked at it, what is a crystal that we have looked at, then symmetry, what is symmetry, okay, and then we have seen that around lattice also we have a symmetry. There are some symmetries which we can see associated with motif, okay, because only motifs with these symmetries are consistent with the one-dimensional periodicity. Okay. Then we have seen point group symmetry, because point group what are the symmetry operations which we have? One-fold, two-fold and mirror. Okay. Generally point group symmetry is nothing but a combination of these operations. One and m is just nothing but mirror. 2 and m is what it turns out to be 2 mm, okay, then a two-fold, then mirror alone can be there. So that is how when we look at it, we have all these 5 point group symmetries. Then when the glide operation comes into it, similar to space group symmetry, we have in one dimension 7 one-dimensional symmetry is there, one-dimensional group. Whether to call it as because space group you can't use it because one dimension you call it as a space or not. If you call it as a space, we can say one dimensional space group. Okay. Here I had given some examples of few patterns. Okay. What I want you people to work out is what is the lattice parameter, what is the one-dimensional lattice which is present on this, what is the symmetry which is associated with these designs, okay, the symmetry of the lattice and the symmetry of these various types of designs. Okay. With this we will stop discussion on one-dimensional lattice. In fact, in one-dimensional lattice we can have many other patterns, like we have taken an asymmetric pattern as a dark P, which is a dark written in dark. We can write it in red. Then if we put them together, then there are many types of patterns which can be generated. Where these patterns become important, not only in crystallography, if you look at the tiling of the floor, okay, architecture, everywhere symmetry is a concept which is very important. Okay. Symmetry actually lowers, okay, that the higher the symmetry, the lower the or the stabler the in stable situation in which the system remains. Okay. Now in the next class we will talk about 2D lattice. Okay.